95% of AI initiatives fail to reach production. The reason? Most of them are built without first principles foundation, and as a result, implementation gaps occur. To address such implementation gaps, working professionals and organization leaders must master the foundational concepts of AI. The first and important part of that is understanding of semantic search. In this video, we'll break down how semantic search differs from traditional keyword search and how vector embedding is the key to scalable AI solutions. But before exploring semantic search, we need to understand that if our system doesn't understand what user's intent is, everything built on top of it will fail. And it's the reason why traditional search engines like Google feel outdated nowadays compared to AI-powered search like ChatGPT or Gemini. First things first, let's try to understand what's the logical concept behind traditional keyword search. For example, a user wants to search about Everest by making a query. There are 5 options with each of the sentences extracted from different documents. Now in traditional search, options A, B, and D contain those exact word matches and are matched even though option C is also relevant here. However, as soon as the user just changes the query by adding mountain at the beginning, the whole scene changes. The exact word match for Mount Everest is only found in option A, and as a result, just option A is matched correctly with the query. This is one such limitation of keyword search. Now, in semantic search, however, intent and context is given more importance, and as a result, options A, B, C are matched correctly that all refer to the same thing, that is Mount Everest. In this video, we'll try to explain how semantic search works and why this simple concept is a big deal in AI production. Before diving deeper into the why and how, I just want to make sure that our focus text and real use case topic for this video will be based towards cloud computing and reducing related costs. So keep that in mind. Also, we will explore why semantic intent routing is important in real-world scenarios, which is crucial for organizational leaders. As a professional or leader, you want to build a tool that can understand a user's questions well, based on your organization's context, data, and guidelines. By doing so, the tool can answer questions itself, route work to respective people or other AI agents. This is where semantic search comes in. Retrieving information to respond to a question and doing a proper routing to people or AI agents, which is only possible when the tool truly understands the meaning or intent of the question. Every resource and knowledge worker as well in the organizational structure. But before diving deep, let's understand what exactly is this semantic search if we think intuitively. Semantic search is a search technique that finds information by understanding the meaning of a particular question based on the language and semantics that we use in our daily life. To further understand this, let's go back to our traditional keyword search. If we have a certain text as reduce cloud cost and 3 relevant sentences, then the first 2 options are said to be matched with the text simply because they contain those exact same words. However, when we simply change the given text to something more intentionally similar text just by introducing new words, then neither of the 3 options match with the new text. Although all of these sentences are conveying the same intent, keyword search can't determine that. Semantic search addresses this problem in an efficient way. There are AI models trained to convert any user input like text into a long list of numbers representing the intent of any information. Mathematically, such a long list of numbers is what we call vectors, and such AI models are called vector embedding models. We can also have input like images and audio, but we will stick to text simply for this demonstration. Now let's convert some of the earlier text that were relevant into vectors. One key thing to note here is that when the text such as reduce cloud costs are converted to vectors, each number in that list represents a unique point or coordinate. These coordinates have special mathematical significance. If the coordinates of any two vectors are highly different, just like the last two ones here, they are far from each other in a 2D mathematical space, whereas the first two vectors here are similar, representing similar intent. That similarity in coordinates helps us to map the first two texts together in the mathematical space, whereas the last text that had a different set of coordinates is far away in this space. The closeness or distance between them is what determines the intent. Here, the term rain cloud, although has a similar keyword cloud as with the term reduce cloud costs, its intent is totally different. That's why it's far from the reduce cloud costs. Similarly, we can also convert meaningful long sentences and paragraphs into vector representation so that we can find the closeness or intent similarity between two different sentences or paragraphs. But in order to find the intent or similarity between two sentences that are converted into vectors, we have two different sets of equivalent mathematical frameworks. The first one is the cosine similarity. If the first sentence is represented by vector A, the second by vector B, and we have a certain angle theta between them, then the theta angle determines how closely the intent of these two vectors are. A high theta value means they are completely different to each other in terms of intent. Low theta value means they are almost similar to each other. This is also done more mathematically using the dot product. By multiplying the individual components of two vectors, we get a precise similarity score. In this case, we get it 0.936, proving these two sentences mean nearly the same intent. This value is close to what we got by doing cosine similarity as well. For instance, let's go back to our example. If we search for the text Mount Everest, the system ranks several options based on their similarity score. Mount Washington might score 0.89 because it's a mountain, while Tokyo scores 0.14 because it's city. This score leads us to a representation of how various terms are related to each other, and such a visual representation is also called semantic vector proximity. It's a technical term, but we can understand it. Now, let's modify this Mount Everest term with a complex sentence query, changing the options. As the query's intent is more directed towards learning mountain climbing, the second option in this case will have a higher similarity score. You can pause the video if you wish to. Again, let's rephrase the query a bit more precisely. Even if we change the query's intent is still similar to the second option, therefore still maintaining the higher similarity score. But what if we wish to make the intent a bit more directed towards arts, visuals, and aesthetics? Then the condition fully changes. Now the option 4 starts becoming more relevant due to its similar intent, leading to a higher similarity score. If we further change the intent, and this time more directed towards technical skill, then the option 2 starts to become relevant again, as the intent is more focused on learning and skills. Finally, let's look at a production scenario that is more relevant in a real use case. For example, if the core team wants to know why did our cloud bill spike last month and how can we reduce it, the semantic system evaluates available AI agents. And the cloud cost optimization agent gets the highest score of 0.96. But look what happens when we just add one more word efficiently at the end. For a little bit of context, now the DevOps agent also gets a really high score of 0.965 that is almost similar to the cloud optimization agent. Now in such a scenario, the semantic system itself can determine which agent to choose. Since the scores are almost equal, there is a necessity for a reasoning model such as LLM to determine the best context and choose the relevant agent. Now, let's try to visualize this theme in the chart that we showed earlier. In this case, there is an additional reasoning model at the top, in our case an LLM, that helps us to route the user input according to the needs. In our next video, we'll dive into the foundational concepts of LLMs that we showed here. But that's it for today. I hope you liked this video. Furthermore, if you would like to build meaningful AI solutions and learn foundational concepts like retrieval augmented generation, RAG, there is an upcoming circle of RAG that you can join in our platform. Later in the series, we will also expand on our vector discussion by exploring vector databases together with the RAG. Make sure to visit careerlink.ai for more such AI-related contents and use cases.